When numerous things have to be right, and by that I mean it have to be exactly the way they are in order for things to work, the likelihood of chance being the cause of that is essentially zero. In other words, the idea is that when you're looking at something that has incredible complexity to it, and you start looking at things that are interdependent, your probabilities become extremely remote. Now, let me show you how, as a physics teacher, I would prefer to approach this. Here are a couple of equations that kids learn in any elementary physics class. Normally, it would be 10th or 11th grade in high school. The first equation that you're looking at is an equation for gravity. F is the force of gravity. M1 and M2 are the masses of two objects that attract each other gravitationally, and X is how far away they are. Now, in order for that equation to be true, in order for it to work, there is a constant, a proportionality constant, which is called the universal gravitational constant. And we've written the value on the screen, 6.67 times 10 to the negative 11th. In order for an atom to exist, the force of gravity has to be within certain limits. If you change that numerical constant by any small amount, modifying the equation and the force of it, an atom couldn't exist. If gravity is too large, matter tends to collapse into a black hole. If gravity is too small, matter tends to fly apart. Another equation that kids learn in an elementary physics class when they study electricity is called Coulomb's law. F, again, is the force, but this time it's the electrical force between two charged objects, like an electron and a proton. Q1 and Q2 are the values of the charges measured in coulombs. And X is how far apart they are. It's an equation that has the same form as the one for gravity. And again, there's a constant, K, 9 times 10 to the 9th. Now, if you change K, you have problems with matter. If K is too large, then particles that have the same charge would be repelled too quickly. If it's too small, they wouldn't be repelled enough. The value of K is critical. And by the way, lots of interesting stuff here. I mean, if you compare the value of G in the gravitational equation with the value of K in the electrical equation, you can understand why we have electric motors and not gravity motors. But what's important is to understand that these constants all work together along with the third equation, which has to do with the force due to motion, to allow such a simple thing as an atom to exist. A hydrogen atom with a proton and an electron, that cannot exist unless those numbers are within a certain range. Now you say, well, you got two equations, two numbers, that's no big deal. Well, it's not just two equations with two numbers. There are magnetic constants. There are coupling constants. There are nuclear constants. As a matter of fact, there are 47 different constants, like the two that I've shown you, that have to be exactly what they are. And like Behe's work with biochemical systems, to suggest that somehow these could happen by trial and error, by some kind of a chance process, is not a workable solution.